Welcome everybody, my name is Alberto Marquez and this is the second video in the series about queuing theory. A very important result is Little's law. We already saw this formula before, but it's important to have it in mind. Little's law is the relation between the number of clients in the system and the total waiting time by means of the arrival rate lambda. The same thing happens for the just the number of people in line or the number of clients in line compared to just the waiting in line. So now we need to introduce the concept or review the exponential distribution. The exponential distribution is one of the preferred distributions that we will use in our queuing theory methodologies, and the reason for that is because it has a property that is very useful. We call that property memoryless. Let's think. Let's say that you're making a sampling of the arrival rate in front of an establishment, say a bank, and you have measured this and you have determined that the time between arrivals has an average of 1, and this time between arrivals has an exponential distribution. So you may ask yourself a question. After 2 minutes have elapsed since the last observation of a client, what is the expected value of the time for the next client to arrive? And the answer for that is 1 minute. The fact that 2 minutes have elapsed has no effect in the expected value of what is going to come in the future. So continuously it renews. There is no memory of the past. To make it clear, let's consider if there has been 8 minutes since the last observation of a client going into the bank. What would be the expected time from that moment or after 8 minutes for the next client to arrive? The answer is still 1 minute. The fact that 8 minutes has elapsed does not have any impact on the expected value in the future. Usually for arrival rates, when we have arrival rates, we can use this exponential distribution because that's the natural process when the clients do not have a pre-scheduled set of appointments. So if that's the case, each one of the potential clients arrive on their own without knowledge of when the other clients will arrive into the system, and therefore the average waiting time does not depend on what the other clients did. And that makes sense. But when we use the exponential distribution for the processing time, now that the system begins to require some strange characteristics. Let's say that the process is to fix a salad for the clients. And each client comes and orders a salad that may take different time. And let's say that the average service time, the average time to prepare that salad is, let's say, 2 minutes. So let's say that you've been fixing this salad for this client who's waiting there for you. He's already started the service and 2 minutes have elapsed. How much longer we could expect for that salad to be fixed? 2 minutes from that moment. In other words, the fact that already 2 minutes have elapsed do not affect the fact that the expected value from that moment on, it'll be 2 minutes. Let's say that you've been fixing the salad for 5 minutes. How much longer do you expect to have the salad fixed in how much long time? That expectation is 2 minutes. So memoryless works well for the time between arrivals. It doesn't work very well for an understanding of what typically happens in a process, a service process or manufacturing process. However, the reason why we use them is because it's the easiest way to account for the events of clients coming and clients departing from the system. Do not affect how much longer will it take for the next client to come and how much longer will it take from this customer to be served. So we use memoryless for those reasons. The exponential distribution has certain characteristics. First, the arrival rate or the service rate or the number of events per time is denoted by lambda. Or in the case of the servers, particularly for queuing theory, we use mu. The domain, that is the possible values for which we can compute a probability, is from 0 to infinity. We cannot go back in time and have a negative time. It is from this moment on into the future. The probability density function is lambda times e to the negative lambda times x. And that is depicted in the graph to the right, on the top right. The cumulative distribution function is 1 minus e to the negative lambda times x, and that is depicted in the graph to the right bottom. The quantile or inverse of the function, and that is going to be very useful for us in simulation, is the negative natural logarithm of 1 minus the function divided by lambda. The mean is denoted by beta, and it can be computed as the inverse of the rate, lambda to the -1. The median is lambda to the -1 times the natural logarithm of 2. The mode, the most likely, or the most probable event, happens at t equals 0. And the variance of this distribution is beta square, or lambda to the -2. So how does the MM1 works? Well, we can compute when we have an MM1. Remember, it's a memoryless baud or exponential baud at the time between arrivals and the service time. And the expected value of the length of the number of people in the system, the number of clients in the system, can be computed as rho divided by 1 minus rho, or that can be re-expressed as lambda divided by mu minus lambda. Rho is the utilization of the system, lambda is the arrival rate, mu is the service rate. Similarly, we can compute the number of clients waiting in line as rho squared divided by 1 minus rho, or lambda squared divided by mu minus lambda. Due to the use of Little's law, we can easily compute the waiting time as L divided by lambda, and the formula can be expressed also as rho divided by lambda times 1 minus rho, or the inverse, the reciprocal of mu minus lambda. The waiting in queue can be computed as the number of people in queue divided by lambda, or rho squared divided by lambda times 1 minus rho, or rho divided by mu minus lambda. An important computation we can get is the probability of having exactly a certain number of clients in the system. And so we can compute, for instance, the probability of having exactly 0 clients. And the probability of having 0 clients, we would have rho to the 0, and naturally it's just p0. But if we wanted to compute what is the probability of having exactly 1 client, it would be p0 times rho. Rho to the 1 is just rho. The probability of having, for instance, 5 clients, it would be p0 times rho to the 5. So we can compute every single one of the probabilities that comprise these, that describe this system. And just as a reminder, the expected number in the system is just a weighted average of that number of customers. So L is just I times P sub I, and a summation of all those terms from having 0 customers to have an infinite number of customers. Of course, you don't have to do the addition of all the summation of all these infinite number of computation or factors because you already have a formula at the beginning of this page. We have other models. For instance, the MMC. The difference between the MM1 and the MMC is that C could represent more than one server. And if that's the case, the very first thing that we need to do is we need to compute the probability of having 0 clients. To compute that, you will see now the formulas begin to become way more complicated and time consuming, because now the nature of the behavior and the number of clients in the system, it is just more complex. So this is the probability of having 0 clients in the system. From that, we can compute now the probability of having a specific number of customers in the system. We have two distinct formulas for that. One formula is useful when we have from one customer up to the number of customers equal to the number of servers, and that probability has to do with the fact that the clients are still not making any lines. And then from that moment on, the behavior changes a little bit, because we are going to have a line if n is larger than c. So at that moment, the formula has to be different, because at that moment, the probability of having to wait in line begins to happen, and at that point, the servers do not keep increasing the number of available servers, and the formula has to change. Once we have B0, we can compute the number of clients in the queue with this formula. Once we know the number of clients in the queue, we can compute using Little's law the average waiting time in queue. Once we know those, we can just add the service time, which is the reciprocal of the rate, to the waiting time in queue to obtain the total waiting time. And then we go back again to use this type of concept to compute the total number in the system. That is the total number of people in the queue plus the total number of clients in the servers. So this concludes the explanations of the formulas for queuing theory. In the next video, we will solve some problems.